All right, guys, welcome back. So today we're looking at 12.4, which is the dot product of two vectors. So the dot product of two vectors essentially is the vector multiplication. I have vector A times vector B, and it's going to be a scalar value, not another vector. We're doing A dot B is A1, B1 plus A2, B2. You're just multiplying the appropriate corresponding locations of your two vectors. So if we had a three-dimensional vector, it would just be A1, B1, C1 multiplying together, A2, B2, C2. Oh, sorry, those three vectors. So sorry, A1, B1, A2, B2, and then A3, B3 for your third piece of that. We're going to do everything in two dimensions, though, for the dot product. We'll talk about three dimensions with our cross products. Now, if the dot product happens to equal 0, and neither vector is the zero vector, meaning there are all zeros there, then the two vectors are perpendicular to each other. Another word for that when it comes to vectors is called orthogonal. So we've got these two vectors, and here's what I was talking about in those other videos with the linear combination. I'll either give it to you in component or linear combination format. It's the exact same process. So if I want to do for A, U dot V, we're going to do 3 times negative 4 plus 6 times 2. Negative 12 plus 12 is 0, so this is orthogonal because the dot product is 0 and neither vector were the 0 vector. For B, U dot V, so we would be doing 2 times 8 plus 5 times 4. When it's in that linear combination format, the I components multiply together and the J components multiply together, and if it was three-dimensional, then the K components would multiply together. So we would get 16 plus 20, which is 36. So because that's not 0, that's clearly not orthogonal. So again, it has to be a 0 product if it's going to be orthogonal. If it's not, then it's not. Again, all orthogonal just simply means the two vectors are perpendicular to each other. When the dot product is a positive value, like we have going on here, you're going to find that that angle happens to be, rather than being perpendicular, it's going to be somewhere between 0 and 90. If the dot product happens to be a negative value, you're going to see that it's going to come out to be more an obtuse angle instead. We'll get more into that as we use more dot product properties. So just a couple things. It is cumulative. The order does not matter for your dot product. Distributive property does work. So if you're adding two vectors together and doing a U dot that sum, you could do two different dot products instead. Multiply the scalar. You could distribute the K to either U or V for the dot product. Doesn't matter. Just make sure you don't do it to both. And obviously a 0 vector is just simply 0 times any vector, giving you just simply 0. Now that angles, this is what I was kind of talking about before with the whole whether you're going to find out it's going to be an obtuse or acute angle here. It's all about based off the dot product. So if the dot product, which is the numerator there, is positive, it's going to be an acute angle. Dot product's negative, it's going to be an obtuse angle because that goes back to the inverse cosine rules. So again, the top is the dot product. The bottom is the magnitude of each individual vector multiplying together. So that's key. Make sure you find both magnitudes and they multiply together on the bottom. So here we're going to find our dot product first. U dot V would be 6 times negative 4 plus 2 times 3. We get negative 24 plus 6, which is negative 18, which tells me I'm going to have an obtuse angle when I do this. Magnitude of U would be the square root of 6 squared plus 2 squared, which is square root of 40, which would be 2 squared of 10. And the magnitude of V would be the square root of negative 4 squared plus 3 squared, which is square root of 25, which is 5. So our angle would be the cosine inverse, don't write tangent inverse, cosine inverse of negative 18 divided by 2 root 10 times 5. If we clean it up a little bit there, it's the cosine inverse of negative 9 or 5 root 10. Either way, though, whether you clean it up or not, your calculator's going to have to do all the work for you. This is generally not going to create a unit circle scenario. It could, and if it does, then you should recognize that. But obviously, we're clearly not. We're getting root 10s, 9s, and 5s, all that loveliness. So we can get 124.7 degrees. It's really 6.9, but after that, it's a number that makes it round up. So that's why we're just going to ignore that and just go 0.7 degrees instead. So again, you notice negative dot product gave us an obtuse angle. Now, if it happens to be in the component format instead, it doesn't really change the process at all. It's still U dot V. So that would be 3 times 3 plus 2 times negative 3, 9 minus 6, which is 3. Dot product is positive, therefore this one's going to be an acute angle. And then we go ahead and find our magnitude of u, which is the square root of 3 squared plus 2 squared, which is square root of 13. Can't do anything with that. Magnitude of v, 3 squared plus negative 3 squared, square root of 18, which is 3 root 2. So we go ahead and find that angle. We'd have the, I keep on writing tangent. Just so used to that from all the other stuff. It's cosine inverse of 3 over root 13 times 3 root 2. Again, if you want to clean it up a little bit just to make it easier to type in, this would then be 3 root 26. So the 3's would cancel. So it's really 1 over root 26. Either way, cleaned up or not, you're going to get 78.69 degrees for the angle in between those two vectors. All right, so just make sure you're careful with that process. Now, whether the angle is acute or obtuse, that's going to be very important to recognize without even calculating the angle here, which again is all about the dot product. We're going to talk about the vector projection right here. So vector projection, you have u and v are non-zero vectors. W1 and W2 are vector components of this u, such that W1 is parallel to v. It's not necessarily going to be the same length as v, but it's in the same direction as v. Or it could be in the opposite direction because it's parallel. And that's where the angle is going to come into play for that. This vector W1 is called the vector projection of u onto v. So what we do is we do the dot product of u times v, and then we're going to do the magnitude of v squared, and then we're going to multiply this whole thing by that vector v. Now, if the dot product happens to be a negative value, you're going to find that W1 is not going to be in the same direction as v, it's going to be the opposite direction of v. That doesn't change any of the calculations, so you don't need to stress over that. We will talk about two examples, one where it's positive, one where it's negative, but just something to consider, then it's just the opposite or the same direction, whether the dot product is positive or negative. All right, so we're going to go ahead and find this W1. So first thing we got to do is we're going to find u dot v. So it's going to be 3 times 5 plus 2 times negative 5, 15 minus 10, which is 5. Now it's projection of u onto v, so we're going to find the magnitude of v. And that's very important. Make sure you're doing the correct magnitude portion. Dot product doesn't matter, but the magnitude on the bottom and then the vector you multiply by is based on this onto that. Whatever it's onto, that's when that goes into the problem. And typically, I'm not going to try and trick you by doing v onto u. It's simply going to be u onto v. So it's 5 squared plus negative 5 squared, which is root 50. And because we're going to square that, I'm not going to simplify it. I'm going to leave it as root 50. Because when we do this projection, W1 is our u dot v, so our 5, divided by our magnitude squared, which is easier to leave it in the unsimplified radical form, and then multiply by the vector v. So again, whatever is being onto, that's also the vector that's multiplying outside of all that. So we go ahead and get 50, square root of 50 squared is just 50. 5 over 50 is 1/10. So it's 1/10 times the 5, negative 5, which gives us 1/2 comma negative 1/2. So that's our vector projection. And then the directions also want us to write u as a sum of two orthogonal vectors, which if you go back a second, u is equal to W1 plus W2. So we need to know what this W2 is. Well, luckily, we already know what u is, and we just found W1. So W2 is really just going to be, quite simply, u minus W1. U is 3, 2. W1 is we just found the 1/2, negative 1/2. So this W2 value is going to be 3 minus 1/2 is 5/2. 2 minus a negative 1/2 is also 5/2. So the way that they want us to do this, u is going to be W1, 1/2 comma negative 1/2, plus W2, 5/2 comma 5/2. So looking to make you split it up into the two components, W1 and W2. A little weird because obviously we already have u, but we just need to find those two different pieces. W1 is the vector projection calculation, and then W2 is just simply vector 1, that W1 subtracted from the u that we want to work with. All right, now again, you saw here the dot product was positive, so this was in the same direction as your v. You're noticing it's 1/2 comma negative 1/2, v is 5 comma negative 5. They're going in the same direction. So if we take a look at this one right here, so we want to find, again, the vector projection of u onto v. So same process, u dot v first. So it's 4 times 2 plus negative 3 times 6. 8 minus 18, we get a negative 10. So this is going to go in the opposite direction then. We have to find our magnitude of v. So it's the square root of 2 squared plus 6 squared, which is root 40. Again, we're going to leave it in the unsimplified form, making our life a little bit easier. And then W1 is going to be that dot product negative 10 over the square root of 40 squared times vector v, not parentheses, let's fix that. 2, 6, I'm going to write it into its component format rather than the i's and j's, just a little bit easier to write out right here. We get negative 10 over root 40 squared is 40, so this is a negative 1/4. Multiply with 2, 6. And we get a negative 1/2 comma negative 3/2. What you'll notice is the exact opposite direction of what we originally had. Making sense that, again, u dot v is a negative, so we're going to be going in the opposite direction. It's still parallel, but it's if you were trying to find the angle in between these two, you would still get a 0, but it would just be, again, or maybe 180 in this case because it's opposite direction. But either way, nothing changed about the calculation. It's just a simple matter of it's in the opposite direction or not. So if they ask a question of same or opposite direction, you're looking at u dot v, positive versus negative. All right, so then we need to find our W2 to then be able to write it as u is the component of W1 and W2. So W2, again, is u minus W1. So it'd be 4 negative 3 minus negative 1/2 comma negative 3/2. So again, I typically like writing component forms, just easier I find. Rather than the i's and j's, you can write whatever format you want. It's not ultimately going to matter. So 4 minus a negative 1/2 becomes a 9/2. Negative 3 minus a negative 3/2 is still going to be negative 3/2. So then we go ahead and say that u is equal to W1, negative 1/2 comma negative 3/2, plus W2, 9/2 comma negative 3/2. And that's our work with our dot product. So one last thing with our vectors, or what we're going to talk about, is the cross product. And this will review the idea of determinants from matrices way back when. So we'll talk about how to do that by hand, as well as using the calculator for certain parts of that. So I'll see you guys next time.